Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. And as I warned in the daily weather update, this will be rather math intensive. And when it's all said and done, you may wonder, why did he waste all that time talking about something that insignificant? But that's the way geeks are. So I did want to share it with you for those of you that are into this type of thing. If not, it's probably Miller time and we'll do the next bonus video for you on Friday. All right, so let me put myself down in the corner here. And remember, we've talked about thicknesses a lot. And there's a mathematical equation that helps us to relate thickness to the average temperature of the layer in between two surfaces of constant pressure. So here's a little math review. This equation looks like this, that the natural log of pressure 1 to pressure 2 is equal to the gravitational constant, which is the rate at which objects accelerate toward the Earth due to gravity, divided by a gas constant, which is R, times the average temperature of the layer between P1 and P2, times the thickness, or the distance between those two surfaces of constant pressure. So R, the gas constant, and don't worry about the units here. It's just that if there's a scientist watching this, it's very important in the scientific community to always have units. And so for those of you that don't care about that, don't worry about it. But I wanted to make sure that scientists out there knew that I knew what the units were. So 287 joules divided by kilograms times degree Kelvin. The gravitational constant is 9.8 meters per second squared. We're going to say that P1 in this case is 1,000 millibars, which is near the surface, and P2 is 925 millibars, which is maybe 2,500 to at most 3,000 feet above the ground. And we're going to say that we're going to do this with two different temperatures. And you have to do this in Kelvin because that's the way the equations work. So 273.15 is the same thing as 0 degrees Celsius or 32 degrees Fahrenheit. So I'm going to have one case where the temperature is freezing, 273.15, and then a second case where we're going to bump it up 1 degree Kelvin to 274.15. All right, so here we go. Let's plug in some numbers. So the natural log of 1,000 over 925 is equal to 9.8 times 287 times 273.15 times the thickness. Now, the natural log of 1,925, or divided by 925, is 0.07796. And the ratio of 9.8 to that other product there is 0.000125 times the thickness. So, for a temperature, an average temperature of the layer of 32 degrees Fahrenheit, or 0 degrees Celsius, the thickness between 1,000 millibars and 925 millibars is 623.63 meters. Now, let's bump up the temperature 1 degree Kelvin, which is the same thing as 1 degree centigrade. And so now when we do the math, the thickness turns out to be 625.92 meters. Okay? So, by changing the temperature 1 degree C, 1 degree C is equal to 2.29 meters, and I'm actually revealing this out of order here, I apologize. So thickness 1 was 623.63, thickness 2 was 625.92. So that's a difference of 2.29 meters corresponding to 1 degree Celsius, and 2.29 meters, if you change Celsius to Fahrenheit, is going to be 1.27 degrees Fahrenheit. So for every 2.29 meters increase in thickness, the average temperature of the layer is going to go up by 1.27 degrees Fahrenheit. Okay, you with me so far? All right, so yesterday's forecast, the ensemble mean forecast for the maximum temperature, this is the American ensemble, for the max temperature yesterday, this was based on data from 7 a.m. yesterday morning, was 50.9. The ensemble mean forecast temperature for today was 54.8. That represents an increase of 3.9 degrees. Yesterday's high was 53, so the implication for today was 56.9. Okay, so I'm taking a look at not the actual raw numbers, but how much is that raw number changing from yesterday to today, and then applying that difference to whatever the high actually was yesterday. So that would have implied 56.9. Now, using the thickness technique, the 24-hour forecast thickness change from 7 a.m. yesterday to 7 a.m. today was 10.9 meters. The 24-hour forecast thickness change from 7 p.m. yesterday to 7 p.m. today was 4 meters. So that averages out to 7.45 meters. And you divide that by 1.27, because we know that 1.27 meters is equal to 1 degree Fahrenheit, and you get 5.9 degrees. That implies a maximum temperature today of 58.9. And the max today at Centennial was 58, and at RDU it was 60, so the 58.9 was right in the middle. So looking at the raw numbers, it actually went a little bit cooler than it actually turned out, but by using the thickness changes, we actually were right in the middle of the actual range today, 58 to 60. I know we're quibbling over a degree or two, and most people aren't going to notice that. I probably wouldn't notice it either, but it's just one of those things where I've had some luck with using the thickness technique being superior in many cases to actually looking at the raw numbers of the model, be it a deterministic model or an ensemble mean. So I just thought I'd share that with you. It's just something sort of fun to look at every day. And what I'm doing for the next 7 days is using this thickness technique for tomorrow and Friday and Saturday. And then I'm going more with the ensemble mean on Sunday and Monday because I think there's going to be a lot of clouds, and the thickness change doesn't take that into account. It's assuming that it's going to be a fairly sunny day. So I've gone more with the ensemble mean on Sunday and Monday with the expected rain, and then going back to the thickness technique on Tuesday and Wednesday when I think we're going to get the sun back at least to some degree. So, all right, hope that makes a little bit of sense. Hope you found that interesting. That is the bonus weather video for this Wednesday, and we'll be back with another one on Friday. In the meantime, have a great Wednesday evening, everybody, and we'll talk to you soon. Take care.